this chart shows us 1,5-AG levels on the y-axis and the different diabetes types along the x-axis. And the first thing to say is that we did replicate that 1,5-AG levels are lower in HNF1 alpha mode than in type 2 after adjusting for HbA1c. But actually, they were pretty similar to the autoimmune diabetes groups. So there's one subgroup of diabetes that's missing off this chart, and that was an unexpected finding that if you actually put the glucokinase mode levels on the graph, it's significantly higher in glucokinase mode than it is in any of those other kinds of diabetes. And that was highly significant. So the 1,5-AG levels in glucokinase mode were actually similar to those in non-diabetic people, suggesting that they have much less glycosuria than any other kind of diabetes. And actually, when you think about the sort of mild postprandial rise of glucose in glucokinase mode that we already know about, it's not that surprising because they don't really put their blood sugar up high enough to reach the level at which glycosuria significantly occurs. Now, if we start looking at some ROC curves for our data, to discriminate between HNF1 alpha and type 2 from our data, the area under the curve was a bit disappointing at 0.6, although that was in unadjusted data, and if we corrected for HbA1c, which was in a way similar to what you guys did, it did improve to about 0.75. If we looked at glucokinase versus type 2, again, that was quite reasonable at 0.79. And then using it to discriminate glucokinase and HNF1 alpha, because if you think about it, the 1,5-AG is going in different directions in those two subgroups. That actually gave an even better discrimination, 0.86. So to summarise that, looking at the two data sets, there's general support that 1,5-AG levels are lower in HNF1 alpha mode than in type 2. And this is strengthened by limiting or adjusting for HbA1c, which of course is correlated with 1,5-AG. Serum 1,5-AG levels appear to be higher in glucokinase mode, and really it warrants further investigation as a tool for identifying and differentiating MODY subtypes, and that's something that's still ongoing because the assay has been very difficult to get hold of in Europe, but now we have a new ELISA that we might be able to do more investigation with. And I think probably the most promising role for this will be to differentiate glucokinase and HNF1 alpha mode, where before we might have used OGTT, this will be a simpler test. So, work in progress. Okay, now to go on to talk about something else. We're looking for the next biomarker, and then in 2008, there's some genome-wide association studies looking at what are the genetic influences on highly sensitive CRP levels. And so this is, just to orientate you, this is a Manhattan plot from one of those GWASs. So up the y-axis is the minus log of the p-value, so the size of the effect. And across the bottom are all the chromosomes. And looking at the SNPs that are associated with highly sensitive CRP levels, it was noted that SNPs near to HNF1 alpha affected CRP levels, and this is in healthy people. Now, again, that wasn't that surprising when we went back to our biology, because we know that the CRP gene is known to be transcriptionally activated by HNF1 alpha and has two HNF1 alpha binding sites in the promoter. And if you go back to your knockout mouse, CRP expression is downregulated by about 18 times in the liver of the knockout mouse. So there was support from the biological data there. So we went on to hypothesize that if you have common variation that's altering CRP levels in healthy people, if you have an inactivating mutation that causes HNF1 alpha MODY, which obviously has a much larger effect on function, those people should have reduced serum CRP levels compared to people with other forms of diabetes. And again, because CRP is something that's very easy to measure, perhaps we could use this as a diagnostic marker. So we did an initial study in UK subjects where we measured CRP in our MODY patients with HNF1 alpha and glucokinase, as well as type 1 and type 2 and non-diabetic subjects. So as you know, C-reactive protein is an inflammatory marker, and we found that 7% of our subjects overall, although quite a lot more of the type 2 subjects had raised CRP. So we presume that this was due to an acute inflammatory response on the day of the test. So we excluded subjects from analysis if they had a CRP greater than 10. And this is the initial data that we published last year, showing that in fact we were correct in our hypothesis that the HNF1 alpha MODY patients had a significantly lower CRP compared to the other groups of diabetes. And also the people who don't have diabetes. So it's not related to diabetes at all. It is actually related to the transcription of CRP. And this was highly significant. But it was only an initial observation in 28 patients with HNF1 alpha MODY. So the next step was that we wanted to go on to replicate this original finding and see if we could establish a highly sensitive CRP as a marker for HNF1 alpha MODY. And just going back to my previous slide, the biggest difference is between HNF1 alpha and type 2 diabetes. Although there is a difference between type 1, this was less marked. And we felt the most promising role of this would be to discriminate from type 2. Again, because CRP in type 2 tends to be a bit higher because of chronic inflammation. So it gave us two directions to make a difference. So the other thing we wanted to do was, because CRP is commonly used, every lab has a different assay. So we wanted to see if this could be replicated across different assays. And ultimately, to try and produce clinical recommendations on the use of CRP in diabetes diagnostics. So we couldn't do it on our own, so we got together with our friends from 7 European centres, from Denmark, Finland, Sweden, France, Norway, Poland, of course, Slovakia, and our samples in the UK. And we added in samples from people with HNF4 alpha, which we hadn't had enough samples to test before. And altogether, we put together over 900 MODY subjects, which doesn't sound like a very large number for an epidemiological study, but for a study of a rare type of diabetes, it's, I think, probably the biggest study that we've managed to put together. So, going on to the methods, as I mentioned, we wanted to compare different assays. So we had measurements from 3 different assays. So samples from Denmark, Norway, Poland, Slovakia and the UK were all measured on the Oxford assay, which we call method 1. Samples from Finland and Sweden and samples from France were measured locally using assays in their local lab. And the difference between these assays, which I'll just highlight, is that although they're all highly sensitive assays, so they go down to a low CRP level, the lower end of the reporting range is actually different between the 3 assays, and that will be important later. Again, we excluded CRP values greater than 10, and that was about 8% of the overall groups, including 7 of the 457 subjects with HNF1 alpha MODY. But nearly 20% of the type 2 diabetic subjects. So the results show that we confirm that CRP levels are lower in HNF1 alpha MODY than type 2. And the way I've represented this is separately for each different assay. So method 1, the Oxford assay, method 2, the Swedish assay, and method 3, the French assay. And what I've shown here are the interquartile ranges, and the medians are on the graph. And just to draw attention that the median values for HNF1 alpha in each group are the lower end of the reporting assay in each case. So they're very low. And this is, of course, highly significant. Now, if you add in the other MODY subtypes, we again see that HNF1 alpha is lower than the other MODY subtypes as well. So that's GCK MODY in purple and HNF4 alpha in green. And we went on to construct ROC curves for each of the centres And you can see that the area under the curve ranges from 0.79 in Finland all the way up to 0.97 in the Danish samples. So across the board, irrespective of centre or assay, this gives good discrimination from young adult onset type 2 diabetes. So we wanted to look at what sensitivity and specificity we would achieve for different cut-offs of CRP. And this is just based on samples that have been analysed using the Oxford assay with the lowest cut-off range. And we found that if you selected cases based on a HSCRP of below 0.25 milligrams per litre, then your sensitivity is 83% and your specificity is 86%. However, in clinical practice, we're probably going to use this in combination with clinical features. So we've looked at various things. But if we took something simple like you've got diabetes diagnosed under the age of 25, so you're very young onset, or you've got a CRP that's below 0.25, you then get a sensitivity that rises up to over 90% without all that much loss in specificity. So that may be the way to use this. Excuse me. And in fact, that would mean that you would sequence all your patients diagnosed under 25, which is more or less what the standard criteria are, but then for the older ones where there's more difficulty, you then go to the low CRP. So to summarise that part of the talk, so this is an example of clinical translation from GWAS. So we've been very criticised for not having immediate clinical translation, but this is a good example. And we've conclusively shown in the replication study that HNF1 alpha MODY subjects have got lower CRP than other forms of diabetes, and we believe we've shown it's a clinically valid biomarker for HNF1 alpha. A great advantage is it's widely available at low cost. It's €1 to €2 to analyse these samples. So that gives it great potential for use in diagnostics. And we're now trying to evaluate this in more unselected data sets. So watch this space. So just now at the end, a little bit of new data, which is still very much work in progress, but just to give you a sort of taste of what this sort of ongoing work is. Just before Christmas, this paper was published in PLOS Genetics, which is again is similar to the CRP story. It's another genome-wide association study, which has identified HNF1 alpha as an important regulator of a biological system. Now, in this case, it's a lot more complicated than CRP because it's looking at the plasma glycome profile. And again, this might not be something you're immediately familiar with, but you'll recall from basic science that most proteins go through a process of glycosylation as a post-translational modification. And this has very important effects on protein function. Proteins can't function without this happening correctly. And there are various disease states where defects in glycosylation are observed. So this study